Alright, so it's working now, guys. I fixed the mic issue. Following the destination and source address fields, 802.3-2008 provides for a variable number of tags that contains various protocol fields defined by other IEEE standards. So because of this additional bytes, 802 provides for a various number of configuration such as the priority, VLAN, additional VLAN, etc. The most common of these are the tags used by 802.1p and 802.1q, which provides for virtual LANs and some quality of service indicators. Maximum of 482 bytes for holding tags. Ethernet originally allowed no tags, just the header, data, and FCS. So for this, there's a restriction. There's a maximum of 482 bytes in this additional VLAN or priority. And Ethernet originally allowed no tags, just the header, data, and FCS. Later, the IEEE added the ability to insert one or more tags, each tag equal 4 bytes. These tags are small data blocks that carry extra information such as VLAN ID 802.1q, priority level 802.1p, service provider identifiers 802.1AD, QNQ, future extensibility features. So aside from priority and VLAN ID, it provides service provider identifiers to actually show or describe its service provider, and future extensibility features in case people wants to innovate and add feature on this. The 802.3 2008 standard says you can have up to 482 bytes of tags in total before the payload. So again, it still starts with the preamble and the DST and the FCS header, or the destination and the source header. These larger frames, that's a theoretical limit. Not every network uses anywhere near that many for this additional capacity for that extended features, priority, and service provider name. These larger frames, called envelope frames, may be up to 2000 bytes in length, but because the tags take up space, the maximum total frame size, header plus tags plus payload plus FCS, was increased from 1518 bytes to 2000 bytes. Again, because tags take up space, the maximum total frame size, header plus tags plus payload plus FCS, was increased. From 1518 bytes to 2000 bytes. So again, because tags take up space, the maximum total frame size, which is the header, tags plus payload plus FCS, was increased from 1518 bytes to 2000 bytes. So because of that, additional configuration, it was increased to 2000, but that's for 82 bytes. It's just a theoretical limit. It can also be used for the IP datagram itself. Envelope frame just means a larger frame that can enclose multiple tags while still carrying a minimum 1500 byte payload. Frames containing 802.1p/q tags, called q tag frames, are also envelope frames. The 802.1p/q standards define the most common tag type, the VLAN/q tag, which is the 4 bytes. So any Ethernet frame that carries a VLAN tag is automatically an envelope frame because it contains at least one tag. So any Ethernet frame that carries a VLAN tag, even if it's a single, is called an envelope frame because it contains at least one tag. Not all envelope frames are necessarily Q-tag frames. This means some envelope frames might contain other kinds of tags, not just VLAN tags. For example, provider bridging 802.1 AD, it adds service provider tags. Just like what I've said, it's just not the priority or the VLAN. It could be the provider tags as well, or the provider bridging. Experimental or proprietary IEEE tags could carry other metadata. So that 4 bytes is not just for VLAN and priority metadata. So not all envelope frames are necessarily Q-tag frames. So all Q-tag frames is envelope frames, but not all Q-tag frames is an envelope frames, but not all envelope frames are Q-tag frame. So here's the visual analogy. Q-tag frame contains VLAN. Basic frame contains VLAN tag, no. Other tags possible, no. Max size 1518 bytes. Description: original Ethernet frame. Q-tag frame 802.1Q contains VLAN tag, yes, the 802.1Q. Other tags possible, maybe. Max size 1522 bytes. Description: VLAN or QoS info. Envelope frame, it contains VLAN tags. It can be or it can be not. Other tags possible, up to 482 bytes total. So when we say envelope frame, that's where the maximum 2000 bytes came in. Max size up to 2000 bytes. Description: new extended frame allowing multiple tags. The 802.3 2008 standard updated Ethernet to support many tags up to 482 bytes worth by defining a larger 2000 byte envelope frame. So it started with 802.3 2008. VLAN tag frames 802.1Q/802.1P are one example of these envelope frames, but other types of tag frames can exist too. Following the fields discussed so far is the data or payload portion of the frame. This is the area where higher layer PDUs such as IP datagrams are placed. So this payload is where the higher layer PDU such as IP datagram or the actual IP or packet from IP. Traditionally, the payload area for Ethernet has always been 1500 bytes, representing the MTU for Ethernet. Most systems today use the 1500 byte MTU for Ethernet. So most systems use this maximum size for Ethernet, although it is generally possible to configure a smaller value if this is desired. The payload sometimes is appended with 0 bytes to ensure that the overall frame meets the minimum length requirements we discussed in section 3.2.2.2. So most system has 1500. If it's lower than that, we append the 0. Frame check sequence, cyclic redundancy check. So the final check of the Ethernet frame follows the payload area and an integrity check on the frame, which is the FCS. So the cyclic or redundant check, which is CRC field, is what comes here. Includes 32 bits and is sometimes known as IEEE/ANSI standard CR32. So 802.3/2008. Basic frame 64 to 1518 bytes. QTAG frames you have 64 to 1522. Envelope frames, that's 64 to 2000 bytes. So in other tags we have up to 48 bytes of tag allowed in envelope frame. QTAG frames are envelope frames. So to use an n-bit CRC for detection of data transmission error, the message to be checked is first appended with n0 bits. So the message to be checked will be appended with n0 bits, forming the augmented message. Then the augmented message is divided using modulo 2 division by an n plus 1 bit value called the generator polynomial, which acts as the divisor. So we append that with n0 bits, and then we it is divided using modulo 2 division by n plus 1 bit value called the generator polynomial, which acts as the divisor. The value placed in the CRC field of the message is the ones complement of the remainder of this division. The quotient is discarded. Generator polynomials are standardized for a number of different values of n. For Ethernet, which uses n equals to 32, the CR32 generator polynomial is the 33-bit number, which is this one, binary, 33-bit binary number. To get a feeling of how the remainder is computed using long mod 2 binary division, we can examine a simpler case using CR64. The ITU has standardized value 10011 for the CRC4 generator polynomial in a standard called G704. If we wish to send the 16-bit message, we first begin with the long mod 2 binary division shown in figure 3.4. In this figure, we see that the remainder after division is the 4-bit value 111. Ordinarily, the ones complement of this value 000 would be placed in the in a CRC or frame check sequence field in the frame. So this is how you check if there's a corrupted data. So upon receipt, the receiver performs the same division and checks whether the value in the FCS field matches the computed remainder. Now what's the big idea here? So every Ethernet frame ends with a frame check sequence. So a 32-bit number, that's 4 bytes. So again, 4 bytes, like the tags, actually is a 32-bit number. It's still a binary. This FCS is created using a special math function called acyclic redundancy check, CR32. So that's what we get in FCS. The purpose, to detect accidental errors like flip or lost bits that may happen during transmission over the network. So where it fits in the Ethernet frame, so we have destination, source, type, payload, and FCS. The FCS field is the C32 checksum. What actually happens step by step? The sender creates the CRC. Before sending a frame, the sender takes the entire message, everything except the FCS field itself. So before sending, it takes the entire message except the FCS field. It temporarily adds 32 zeros at the end since n equals to 32 for CR32. So it adds 32 zero first on that message. It divides this long binary message by a special generator polynomial using mod 2 arithmetic bitwise SOR instead of subtraction. It keeps only the remainder of this division. So by adding that 32 zeros at the end and then dividing that with this long binary by a special generator polynomial using mod 2 arithmetic bitwise SOR, it keeps only the remainder of this division. It flips all the bits that of that remainder, takes the ones complement, and stores that 32-bit value in the FCS field. And then it flips all the bits of that remainder and then it takes the ones complement and store that 32-bit value in the FCS field. So after it does that, it will flip all that and takes ones complement and stores the 32-bit value in the FCS field. So that remainders the CR's C32 value, which allow us to check if it's corrupted or not. So that's the checksum we're talking about. The receiver verifies the CRC. When the frame arrives, the receiver takes the entire frame, including receive FCS. It performs the same division using the same generator polynomial. So it's the receiver used that same generator polynomial. If the result remainder is 0, the data is considered good. If the result is non-zero, the frame is corrupted and will be discarded. So example, using simplified C4, which we discussed using that graph. The book gives a small example with CRC C4 to show how the math works, since here 32 would be too big to show. So message, these are the message with the 4 CRC4, append 4 zeros, generator polynomial 1, CRC4 is 10011, perform binary division, source style, remainder 1111, ones complement 000, that's what would be placed in the FCS field. When the receiver repeats the process, it should get 00 as remainder if no bits were corrupted. So the receiver should get 00 or 40 if no bits were corrupted. What's a generator polynomial? It's just a fancy way to represent a fixed binary pattern used with CRC math. For Ethernet C32, that polynomial is this. So it's just a fancy way to represent a fixed binary pattern used in the CRC math, like this. Or in shorthand, hexadecimal, like this, 0x04C11087. So we can write it as a 32 bits, or we can binary, or we can shorthand it in hexadecimal, 0x04C11D 87. So this polynomial was chosen because it's very good at catching nearly all realistic data corruption patterns, single bit burst errors, etc. So in short, CRC, a mathematical checksum to detect data errors. It's a mathematical checksum. You can also use that in your TCCR C32, the specific 32-bit version used by Ethernet. Generator polynomial, the fixed binary pattern used in the CRC math. FCS, frame check sequence, the 32-bit CRC value added at the end of each Ethernet frame. Purpose, to let the receiver detect if the frame was corrupted in transit. Analogy, think of CRC like a digital fingerprint of your Ethernet frame. The sender stamps unique fingerprint C32 on the data. The receiver checks if the fingerprint still matches. So analogy, think of CRC like a digital fingerprint of your Ethernet frame. It's like a digital CRC is the digital fingerprint of your Ethernet frame. The sender stamps a unique fingerprint CRC32 on the data. The receiver checks if the fingerprint still matches. If even one bit changes, the fingerprint won't match, so the receiver knows the frame got damaged. So the sender stamps a unique fingerprint C32 on the data, and then the receiver checks if the fingerprint still matches from the sender. If even one bit changes, the fingerprint won't match, so the receiver knows the frame got damaged. Now, frame sizes. There is both a minimum and maximum size of Ethernet frames. The minimum is 64 bytes, requiring a minimum data area payload length of 48 bytes with no tags. So that's the minimum size of the payload. In cases where the payload is smaller, pad bytes, which is value 0, are appended to the end of the payload portion to ensure that the minimum length is enforced. So in cases where the payload is smaller, the pad bytes, so the minimum is 48 bytes. If it's smaller, the pad bytes, which is value 0, are appended to the end of the payload portion to ensure that the minimum length is enforced. So minimum frame 64 bytes, MAC header, which is 14, the source and the destination, datapad 46, FCS 4. Maximum standard frame 1518 bytes, this is the maximum. MAC header 14, data 1500, FCS 4. Jumbo frame 9000 bytes, MAC header 14, data up to 9000. Then we still have FCSS 4. So the core idea, Ethernet frames can't be any size you want. They must obey strict minimum and maximum size rules in the standard. So limit minimum frame size 64 bytes. Purpose ensures reliable collision detection in all Ethernet. So it provides a reliable collision detection. Maximum frame size 1518 bytes, basic, balances efficiency and error recovery. Minimum frame size, which is 64 bytes. While there's a minimum, in the original Ethernet, 10 millibytes per second using CSMA/CD. Carrier sends multiple access with collision detection. Computers shared a common wire. If two computers send data at the same time, a collision would occur. So that's the reason why we have a minimum frame size. To detect that collision, the transmitter must still be sending data when the collision signal comes back from the farthest point in the network. So to detect that, a transmitter must still be sending data. If the frame were too short, it could finish sending before the collision is noticed, meaning the sender would never realize the data was corrupted. So the Ethernet designer made sure that by the time a collision could happen and its signal travels back, the sender would still be transmitting the frame. That's what determined the minimum length of 64 bytes. So that's what this note means. So note, the minimum was important for the original 10 millibytes per second Ethernet using CSMA/CD in order for a transmitting station to know which frame encountered a collision. A limit of 2,500 meter, 500 meter cable segments with 4 repeaters was placed upon the length of an Ethernet network. Given that the propagation rate for electrons in copper is about 0.77 C or 231 m meter per second, and given the transmission time of 64 bytes to be 64 times 8 over 10 million is equals to 51.2 U seconds at inverted U second at 10 millibytes per second. A minimum size frame could consume about 11,000 meter of cable. With a maximum of 2,500 meter of cable, the maximum round trip distance from one station to another is 5,000 meter. The designers of Ethernet included a factor of 2 over design in fixing the minimum frame size. So in all compliant cases and many non-compliant cases, the last bit of an outgoing frame would still be in the process of being transmitted after the time required for its signal to arrive at a maximally distant receiver and return. If a collision is detected, the transmitting station thus knows with certainty which frame collided, the one it is currently transmitting. In this case, the station sends a jamming signal, high voltage, to alert other stations, which then initiate a random binary exponential backoff procedure. The math behind it simplified. Network length limit 2,500 meter, 5 segment times 500 meter each. Signal speed 231 million meters per second, 0.77 C. Transmission time for 64 bytes at 10 millibytes per second. 64 times 8 over 10 million equals to 51.2 inverted U seconds. round trip for 2,500 meter cable, about 22 inverted U seconds. The frame is still being sent even after the signal has traveled to the farthest node and back, ensuring collision detection works. If the payload is shorter than 48 bytes, Ethernet adds padding 0 seconds to reach the 64 minimum. The maximum frame size of conventional Ethernet is 1518 bytes, including the 4-byte CRC and 14-byte header. This value represents a sort of trade-off. If a frame contains an error detected on receipt by an incorrect CRC, only 1.5 kilobyte need to be transmitted to repair the problem. On the other hand, the size limits the MTU to not more than 1500 bytes. In order to send a larger message, multiple frames are required. 64 kilobytes, common larger size used with TCP or IP networks, would require at least 44 frames. So maximum frame size 1518 bytes. Why there is a maximum? Too large a frame would mean more data loss if a frame has an error, longer delays before other stations can transmit, hardware buffers and timing become harder to manage. So the designer capped the total at 1518 bytes. So component, destination plus source MAC, the bytes 12, type or length 2, payload MTU 1500, FCS, CRC 332 4, total 1518. So this trade-off keeps retransmission short and ensure fair access. The unfortunate consequence of requiring multiple Ethernet frames to hold large upper layer PDU is that each frame contributes a fixed overhead, 14 bytes header, 4 bytes CRC. To make matter worse, Ethernet frames cannot be squished together on the network without any space between them. In order to allow the Ethernet hardware receiver circuits to properly recover data from the network and to provide the opportunity for other stations to interleave their traffic with the existing Ethernet traffic. So the Ethernet 2 specification, in addition to specifying 7-byte preamble and 1-byte SFD that precedes any Ethernet frame, also specify an Internet gap or IPG of 12 bytes times 9.6 inverted US at 10 millibytes per second, 960 nanoseconds at 100 millibytes per second, 96 nanosecond at 1000 millibytes per second, and 9.6 nanoseconds at 10,000 millibytes per second. Thus, the per frame efficiency for Ethernet 2 is at most 1500 over 12 plus 8 plus 14 plus 1500 plus 4 is equal to 0.975293 or about 98%. One way to improve efficiency when moving large amount of data across an Ethernet would be to make the frame size larger. So because of this, you cannot have the 100% efficient. So because if it's too short, by the time a collision could happen and its signal travels back, the sender would still be transmitting the frame. That's why there's a minimum length of 64 bytes. So we calculate the math behind that, and the maximum frame size of conventional Ethernet is 1518 bytes, including the 4-byte CRC and 14-byte header, which is include the destination and source. This value represents a sort of trade-off. If a frame contains an error detected on receipt by an incorrect CRC, only 1.5 kilobytes need to be retransmitted So if there's an error, only 1.5 kilobytes need to be retransmitted to repair the concern. That's where there's a maximum. On the other hand, the size limits the MTU to not more than 1,500 bytes. In order to send a larger message, multiple frames are required. 64 kilobytes, a common larger size used with TCP or IP networks, would require at least 44 frames. So for 64 kilobytes, we are actually dividing that to 44 frames. So while there's a maximum, too large frame would mean more data loss. If frame has an error, longer delays, and then hardware buffers and timing. So what's the implication of this? Because of the 1500 byte payload limit, larger messages like a 64 kilobytes TCP segment must be split across multiple Ethernet frames, adding some overhead. Each frames include header 14 bytes, FCS 4 bytes, inter-packet gap 12 bytes, preamble plus SFD 8 bytes. So that overhead makes Ethernet efficiency about 98% as shown here. Efficiency equals to 1500 over 12, which is inter-packet gap, the FCS plus 4, the header, destination, the tags, etc., and the preamble plus SFD, which is 8, 0.9753. So beyond the standard jumbo and super jumbo frames, to improve efficiency for large data transfer, some high-speed Ethernet system, especially 1 gig per second and up, support jumbo frame type, typical max 9000 bytes. Notes common in data centers, non-standard but widely supported. Super jumbo frames 9000 bytes, used in specialized research or high-performance networks. These reduce header overhead but are not compatible with legacy 1518 byte devices. So you must ensure all devices in network support them. So summary, minimum frame size 64 bytes, 46 byte data plus 18 bytes header. Reason, guarantees collision detection CSMA/CD. Maximum frame size 1518 bytes, 1500 byte data plus 18 bytes header. Balance efficiency and fairness. Jumbo frames 9000 bytes. Non-standard improves efficiency and modernize. Envelope frames 802.3 2008 up to 2000 bytes. Standardized to allow multiple tags. Padding added if payload is less than 46 bytes. Ensure 64 byte minimum total frame length. So here's the quick visualization. MAC header for 64 bytes is 14. Datapad 46, FCS is 4. Maximum standard frame 1518 bytes. MAC header 14. Data 1500, FCS 4. Jumbo frame at 9000 bytes. MAC header 14. Data up to 9000, FCS 4.